Hi, how are you? And today we'll be going over Chapter 6's exercise 6.12. And the exercise reads as follows. Explain what language this context-free grammar generates with the start variable s, where s goes to a, b, and a, b are non-terminal states. A goes to 0, a, 1, or the empty string. B goes to 1, b, 0, or the empty string. And so when thinking about this context-free grammar, it becomes a little tricky as to how you want to think about the language behind this. And it turns out that the language will simply be 0 to the a power, 1 to the b power, and 0 to the c power, all in that order, because order matters with languages, such that a plus c is equal to b. What that means is if you have the ones in the middle, on either side of those ones, you will have the same amount of zeros as ones, pretty much. But they don't have to be even amounts. So you can have 3 on one side and let's say 4 on the other, as long as there are 7 ones in that case, because there has to be a total of zeros and ones equaling the same thing. So in this example, we take a deep dive into how the machine would actually work and the inner workings of it. And this is kind of fun to look at and interesting. At the same time, there's actually multiple ways of handling this, but I took a whack at it with 2 attempts. The first attempt wasn't as clean and it didn't work for all the strings, so I wouldn't look at it. I'm gonna leave it in here just so you guys can look at it and play with it. Maybe you guys can make something better of it. But the idea behind the first attempt, which is what I'm going to go over right now, just to show you guys a little bit. The idea behind the first attempt is to kind of read the string at 2 inputs. At 2 points. So at 2 halves. So the beginning and the end. So we're going to just keep reading it and working our way in kind of like that. And the reason that first came to mind is because you have this language that is 0 to the a power, 1 to the b power, and then 0 to the c power, which you almost want to think that it's symmetric and you kind of want to work at it from both sides. And that's a fair assumption, and that is doable, except for one caveat that happens in the middle. And I want to go over that right now. So let's say we have, let's say we have 2 zeros, 3 ones, and a 0. So if we have this kind of input string, what will happen is if you're working it from both sides, what I mean by that, I'm going to look at the back right here and the front all at the same time and work my way in. So what this will do is it will look at the front and the back and just remove those strings. And this is what becomes tricky. Now you have that extra 0 in the front, and this can happen from either side. You can have an uneven amount on the front or in the back. It doesn't matter where. This is kind of tricky here. And what happens is you're left with that extra 0, and the next thing that has to happen if you're reading it like this is it can alternate now. And because that alternating part of it, you can have an accidental string that shouldn't be accepted but is. And in this case, you can have an alternating set like 101 that shouldn't be accepted but can be. And that's very tricky. So what I would say is to be careful with this and the way you want to conquer or tackle this context-free grammar language in the form of doing it from both points of the tape or list. So this is possible. You just have to handle this case really carefully. And then if you can handle that case and keep working your way down, working your way down, you'll end up with, ones on each side, and then you can pretty much count those up and have your functioning Turing machine that accepts the proper inputs or strings that we wanted from the beginning. And since that didn't work out because of that caveat, a second attempt was created by me. And I'm going to leave both attempts in, but the second attempt is the one that works. So if you're testing inputs or strings down here, definitely use the first attempt if you want to just play around with it and see if it works. This one's guaranteed to work. The second one, or the first attempt, isn't really guaranteed to work for that caveat, but for everything else it will. So feel free to use that if you choose to. So here's how this problem works in the new attempt, or this second attempt. So we're going to have a count of our zeros and ones. Now notice that the language has a count of A, B, and C. In this case, our C is being handled by the A variable. And this is very interesting, the way it's going to be handled like that. So instead of creating 3 variables, we're going to use 2. We're just going to keep tagging on to that A, because all we want to do is make sure that the A and B, aka ones and zeros, are equal to each other. The amount of them are equal to each other. End of the day, as long as we handle the positioning of the zeros and ones in the input string. And so what happens now is, if we have an empty string that we give this Turing machine, it should accept it. The machine will handle that on its own already, but just for clarity's sake, I threw that in there as an if block, so it's easier to see for anybody that wants to look at the code or play with it. So the actual heart of the Turing machine or program here is that as long as we have a value in the string that is a 0 technically, and the string is not empty, or the input's not empty, we're going to count that as our A block, which means that for all the zeros we're going to read in, we're going to count A's, right? We're going to count it as an A variable. We're going to keep track of the count with the A variable. Sorry, I don't know why that came out so weird. And this is going to read in all the zeros in order. So as soon as we hit a 1, this loop ends. And what this part right here does is it shrinks down the list for us. Like before, I was telling you, we want to kind of work from both ends for the other example. This example, we're only looking at this the one way. We're going from left to right, kind of. And what you want to happen is every time you read in a value, you want to kind of keep track of it, but don't keep it in the string or input. You want to remove it so you don't have anything overlapping, because it's already been read in. Like the important information is being extracted, so we kind of just throw out the actual value. And the reason for this is the Turing machine will only accept, at least this example of it, will only accept a string if it is empty in the end of the day. If it's not, it will not accept it. It will not be valid in the eyes of the Turing machine. So that's the way that this exact program handles it. And so once we've written all the zeros, we're going to go on and read in all of our ones, as long as it's not empty. And if it's not empty and it has ones for us to read, then we're going to keep count with B. And B is going to keep count of all the ones, like we said before. And this follows true with the language of the context-free grammar that's described in this exercise. And now here's the interesting part. The third part is if we have a 0 after that, which we will, as long as we want to, because we want to make sure we have the same amount of zeros and ones from total, but you can have 0, 1, 0 order, kind of like that. So when we read in our second appearance of 0 after all the ones, instead of counting that as a C and following the traditional kind of pattern, we're just going to throw that in with the A's, because at the end of the day, it's still our zeros, and A's keep track of zeros. So that kind of handles our C clause right there. And then after all that's been handled and we read in our values, we make sure that the language is empty, or if it's not empty, it's not going to be accepted. And then we're going to go down here, and if the amount of zeros is equal to the amount of ones, we're going to return true. Otherwise, we're going to return false, which means that it's going to accept or reject the string. And down here, all the way down here, I have some test cases. You can see that for the empty string accepts it. Let's say we have something like this, 0, 0, 1, 1, 1, 0. I think this was the edge case I had for the other one, and notice how it does return true. Yeah. All right.